Welcome to the tutorial on master-slave SR flip-flop. The master-slave flip-flop or the pulse-triggered flip-flop. As I have mentioned in this particular slide, pulse triggering is also called as level triggering. So when I say pulse-triggered flip-flop means I am actually applying level triggering for the master-slave flip-flop. So in this master-slave flip-flop, we have the property of timing of a flip-flop response being related to the control input signal, which is achieved with the master slave and edge triggered flip-flop. So here you have basically two cascaded sections which is each capable of storing a binary symbol. Okay, how that cascaded sections are formed I will show you in the diagram when I consider the example. So the first section is referred to as the master and the second section is referred to as the slave. And the information entered into the master on one edge or level of the control signal and will be transferred to the slave on the next edge or level of the control signal. So the information that is entered into the master on one edge or the level of the control signal will be transferred to the slave on the next edge or the level of the control signal. Since I am discussing the master-slave flip-flops in terms of pulse trigger, here it will be in terms of level triggering. Okay. So each section is a latch. So let me explain this with an example of a master-slave SR flip-flop. Okay. So here, so this is an SR latch, this is another SR latch, and this will be called as a gated SR latch if you can recall, because we make use of an enable or a clock pin. So that is why I can call this as a gated latch, gated SR latch. This is another gated SR latch. So here whatever information is entered into the master on the level of the control signal will be transferred to the slave, okay, on the level of the control signal, okay, that is on the next level of the control signal. So this is the master, this is the slave will follow the master depending upon what control signal you are going to apply. So let us look into much detail with the master-slave SR flip-flop. Remember here I am considering still level triggering. I have not entered into the concept of edge triggering. This is still level triggering, also called as pulse triggering, wherein I am bothered about the level of the clock signal. So here you can see that there are two input lines S and R, because I am trying to understand the concept of the master-slave SR flip-flop. So you have two inputs S and R which corresponds to the set and the reset. The clock signal C is applied to the control input line. So if you can see, for the master-slave SR flip-flop, you have the control signal C being applied directly to the master, whereas it has been inverted and being applied to the slave. So let me first consider that I am applying a clock to be equal to 0. So when the clock is 0, what happens is that the master will be disabled. So this particular SR latch will be disabled and we have an inverter being used here. So since this is 0, you have a 1 that is provided to the slave. So C will be equal to 1 in this particular case. So this slave will be enabled due to the presence of the inverter. So hence what we can say is that the slave will be in the same state as that of the master. Since QM and QM bar are connected to the S and R of the slave. So that is why whatever will be the state of QM and QM bar, same thing will appear across S and R, and because you have a clock 1 here, you will obtain the output as Q bar, which will be dependent upon the output of QM and QM bar. So you can see when C is equal to 0, that is I am talking in terms of the complete master slave SR flip-flop. When you have C is equal to 0, the output Q and Q bar will be the same as that of the master. Now let me explain this in detail with the flip-flop action that occurs during the control signal. So here you can see as the control signal starts to rise, the slave is being disabled, that is this point, okay. Initially when the control signal was completely 0, the master was disabled and the slave was enabled. Whereas now as the control signal starts to rise, what happens is that the slave is disabled, that is at time T1, while the master will remain disabled. Thus the slave becomes disconnected from the master but retains the state of the master. So during this particular point between the interval T1 and T2, the master will remain disabled and the slave will become disconnected from the master but will retain the same state of the master. Now let us see what happens at the time interval T2. So when C is at T2, that is when the clock signal is at T2, the master will slowly start becoming enabled. That is because your value of C is changing from 0 to 1. So when C is equal to 1, the master will respond to the change in S and R signals. So at this particular point, that is when the master is enabled, the slave will become disabled. That has been shown here. You can see that initially clock was 0 and here for the slave clock was 1, that was shown in the red color. Whereas now the clock is equal to 1, which is shown in green, and for the slave the clock is equal to 0. So the slave will become disabled and it will retain the same state of the master, that is Q will be equal to QM and Q bar will be equal to QM bar. The master will be enabled and it will respond to the inputs, that is S and R, depending upon what type of inputs you are going to give. The inputs can be 0, 0, 0, 1, 1, 0 or 1, 1. So it will respond to the inputs. So the same thing has been illustrated here. So as I specified, because we have the slave being disabled here due to the presence of the inverter, any change in the state of the master will not be reflected to the slave. Next, at the interval T3, the master will be disabled. You can see here because this is the falling side, right? Falling edge. So the interval at T3, the master will be disabled, and at T4, the slave will be enabled. So the output of the master will be passed to the input of the slave and you can see the change in the output. So one conclusion in general what we can see here is that only for short periods during the rising and the falling edges, both the master and the slaves are disabled. That is what is being shown here. That is this interval of the time you have the master and the slave being disabled. So as I explained earlier, when C is equal to 0, master will become disabled, slave will become enabled, and it will take on the new state of the master, whichever is being specified. So you have the different combinations of S and R, and you have the clock pulse being applied. So when it is 0, 0, you have Q, Q bar, 0, 1, 0, 1, 10, 10, 11 is undefined state. So if you can recall, this is exactly the same function table that was used for the gated SR latch. The condition where clock can also be equal to 0. So when the clock is equal to 0, or I can say when clock is not applied, then no matter what is the condition of the inputs, that is S and R, the output will remain at Q and Q bar. And here you can see the logic symbols of the SR, wherein it is being specified as Q and Q bar, where Q bar can also be written in terms of a bubble. Now let me explain the concept of the master-slave SR flip-flop using the timing diagram. So here what I am trying to do is, whatever behavior of the master-slave flip-flop is there is being reflected here using the timing diagram. So let me have a comparison of this timing diagram with that of the function table. Okay, so you have the combination 0, 0, and you have the clock pulse that you are going to apply to be 0, and output is equal to 0, 1, and the same thing will be reflected at the output of the slave. This QM corresponds to the output of the master, QS corresponds to the output of the slaves. So whatever is obtained at QM and QM bar, same thing will be reflected at the output of the slave. So the slave will follow the master. Next I have the clock pulse being applied as level 1 or high input. So you have the combination of SR to be equal to 0, 0, and for a combination of 0, 0, you obtain the output of the SR latch to be equal to 0, 1. That is what is being shown in the function table. So when you have output 0, 0 and a clock to be equal to 1, the output of master slave flip-flop will be Q, Q bar. Q, Q bar was equal to 0 and 1. So same thing has been retained in the case of application of 0, 0 with the clock input 1. So since Q, Q bar was 0, 1, you obtain here also to be equal to Q, Q bar, that is 0, 1. Next we have the combination 1, 0 with the clock input to be equal to logic 1. So when you have the clock input to be logic 1 and the combination is 1, 0, if you look at the function table, 1, 0 clock input is 1 and output will be equal to 1, 0. So here the same thing has been explained. You have 1, 0, clock input is 1, output is equal to 1, 0. So in this particular case, what happens is that you should see as to what will be the output of QM and QM bar is equal to 1, 0 that you have seen here. As per the function table, you have 1, 0 combination. When the clock pulse is applied, you have 1, 0. So output is equal to 1, 0. See, if you observe the function table, for the second SR latch, that is second SR gated latch, what happens is that when your master is enabled, what happens to the slave? Your slave will become disabled. So irrespective of the type of the input that appears across the slave, the output will always remain to be equal to Q, Q bar. So the same thing has been specified here. Though I get this as 1, 0 combination and clock input is 1, here I might get it as 1, 0. So S and R will become 1, 0. But clock is equal to 0. When clock is equal to 0, then it follows that irrespective of the type of the input that I get, because the clock is 0, output should be same as that of the previous state, that is Q and Q bar. That is why in this particular timing diagram, because this is 1 0 and this is 1 0, since the clock to the slave is equal to 0, the output will be same as that of the previous states. So this will become 0 1. Next I have 0 0 and the clock to be equal to 1. For a combination of 0 0 and the clock to be equal to 1, the output will be equal to 1 0. Again here for the slave, the clock is disabled. So here output will remain as same as that of the previous state, that will be equal to 0 1. Whereas for the last case wherein I am considering this to be 0 1 and clock 1, I have the condition for which the output will be equal to 0 1. That is because if you look at the function table, 0 1 when the clock is applied, output will be equal to 0 1. So the same thing has been reflected here. When I am applying 0 1 with the clock, I am having 0 1 here, but for the slave the clock is equal to 0. So whatever is the previous state, the same thing has to be continued. So if you observe for the entire time duration, here the previous state was equal to 1 and 0. That is why for this part of the signal, the output will be equal to 1 and. So this way you will be able to compare the timing diagram with that of the function table. So in general, I can say that the behavior of the master-slave flip-flop, which is constructed from the latches, because I mentioned each of this is a latch. This is one gated latch, this is one gated SR latch, will be dependent upon the rising and the falling edges of the control signal if I am considering the positive edge or the negative edge. But in this case, I am considering the level triggering, and also it is dependent upon the period of the time in which the control signal is high. So here you can clearly see in the timing diagram that depending upon the period for which the control signal is high, I am obtaining the relevant output. So I can refer to this type of a flip-flop wherein I am bothered about the duration of the clock pulse to be a pulse triggered flip-flop, also called as a level triggered flip-flop.